Stripping down science. The Naked Scientists.
Hello, it's Sunday the 20th of March. Welcome to The Naked Scientist with me, Ben Valsler. And today I am joined by Dominic Ford. Hi, Dominic.
Hello.
This week we're looking beyond the confines of our universe to explore the ideas of multiverses, string theory and physics at the subatomic scale. Chris Lester will be joining us in the studio to explain what we can learn from the LHC. And Brian Greene introduces us to the idea of parallel universes.
A lot of research from a variety of different directions over the last few decades have suggested that what we long thought to be everything may not be everything. It may be a piece of a larger whole. And that larger whole may contain other universes, and that's where we come to the idea of multiple universe.
Plus, we'll hear from Mira and Dave, who've been to the Diamond Synchrotron to find out about the engineering of an electron accelerator.
And in the news, how quartz makes mountain ranges, Messenger goes into orbit around Mercury, and why birds can't help but to fly into man-made objects. So if you have any questions for us, tweet at Naked Scientists, post on our wall at thenakedscientist.com/Facebook, or drop us an email. Our email address is chris@thenakedscientists.com.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
This is The Naked Scientists with me, Ben Valsler, and with Dominic Ford. And first up, let's take a look at some of this week's biggest scientific breakthroughs. The mineral quartz might hold the key to why continental plates consistently deform in certain regions. That's a puzzle that's remained hard to answer despite revolutions in our understanding of plate tectonics. Publishing in Nature, Anthony Lowry and Marta Perez-Guccini used data from the EarthScope Transportable Array. Now that's a program that's steadily measuring seismic activity across the United States. They use that along with gravity and heat flow data to estimate the relative proportion of quartz in the crust and to look for geographic variation. Their research took the relatively novel approach of mapping the ratio between pressure waves, they're called VP, they're the longitudinal, like sound waves travelling through the crust, and shear waves, VS, they are transverse waves that make the crust move a little bit like ripples on a pond. This ratio is not a measure that's used often in research because it can be inaccurate and it's altered by a number of other factors such as crust thickness. So to iron out all of these inaccuracies, they combined the ratio values with established data from gravity surveys and from estimates of heat flow. The authors argue that a low VP to VS ratio, that's less than 1.8, correlates to high concentrations of quartz in the crust, and that because quartz is fragile and it's prone to flow at the sorts of temperatures found at depth, this actually encourages weak zones in the crust itself. Once these regions of weakness establish a deformation zone, this encourages further weakening processes such as the ingress of water or increased heat flow. Now actually this dynamic system would ensure that the crust consistently deforms in regions of high quartz and could even contribute to a weakening of the mantle layer below the crust, which further ensures a zone of weakness is maintained over many millions of years. Not only does this model elucidate the role of quartz in making mountain ranges, but it could also help to explain some of the more unusual types of earthquake, those that occur in the middle of continental plates, where there's little or no evidence of the fault lines that we usually associate with the more familiar and better understood earthquakes. This particular study only observes an area of the western United States, but the authors do intend to keep monitoring the data as the EarthScope moves east, and it will eventually measure activity across the entire country at 70-kilometre intervals. Also, looking at geologically active regions around the world could give us an even better idea about the role of quartz in sculpting our continents. Dominic.
Well, there have been a lot of headlines this week about the Messenger spacecraft, which has become the first probe ever to be launched into orbit around the planet Mercury. Now, this is actually quite a historic milestone in our exploration of the solar system, because this is the first time that we have actually had a spacecraft in orbit about Mercury able to image the whole of its surface. Now, it's about 30 years since the Voyager spacecraft first visited the outer planets of the solar system, and over those 3 decades, our understanding of the planets of the solar system has really increased, but Mercury has always remained a slightly elusive planet. We didn't actually even have a map of more than half of its surface until Messenger first flew past a couple of years ago. And the reason why Mercury has been so elusive is that it's actually quite difficult to put a spacecraft into orbit around it. And that's because it's so close to the Sun. And if you're launching a probe from the Earth, it has to swoop down through the solar system to get to Mercury. And it's travelling incredibly fast when it gets there. It's like a ball rolling down a hill, going faster and faster. And if you want to go into orbit, you have to be moving slowly enough that you can be gravitationally captured by the planet. So up until now, only one spacecraft has ever been there. That was Mariner 10 back in 1974. But we have a lot to learn about Mercury. It's one of the 4 rocky planets, and we think these 4 rocky planets all started from a fairly similar starting point, but seem to have evolved in very different directions. We know that the Earth obviously seems to be an ideal place for life to develop. Mars seems to be similar, but because it has no magnetic field and a very thin atmosphere, its surface is bathed in solar ultraviolet and ionising radiation, and that makes it difficult for complex chemistry that you need for life, and so that's possibly why we haven't found life on Mars. Venus, we know, has a very thick atmosphere of carbon dioxide. That's led to a runaway greenhouse effect and means its surface is at a temperature of about 480 degrees and really far too hot for us to imagine life being there. But Mercury is the elusive planet because it actually has a very strong magnetic field. Its surface is not as harsh as it might be. It's hot because it's close to the sun, but it's not so hot or so harsh. And we would like to understand where that magnetic field is coming from and about the rocks of Mercury. And it's hopefully in the next few years, as Messenger returns more detailed maps of the surface, that we'll really start to understand this enigmatic planet.
So it's achieved orbit around Mercury, which is a feat in itself, but what's it going to do now? Is it purely mapping the surface, or is it taking other readings as well?
It's looking at maps of the topology of the surface and also at the chemistry and the geophysics. So looking at whether you have volcanoes and so forth on the surface, and that will help us to understand what this planet is made of. We think it possibly had quite a violent history because we think it must have quite a large iron core at its centre to give it its magnetic field. And that would suggest maybe it's an Earth-like planet which has lost most of its mantle of rock and is just the iron core at the centre that's left.
Well, thank you very much. We'll look forward to hearing a bit more about it. Also this week, a pair of papers in the journal Nature have shed some light on how human sperm cells react to the presence of progesterone, and this could lead to a whole new type of contraceptive. Steve Publikova from the School of Biosciences at the University of Birmingham penned a News and Views article linking the findings of these 2 papers, and he explained the implications to me.
It's been known for more than 20 years now that progesterone, female hormone progesterone, which is produced by the cells that surround the oocyte, and they help it to mature, and they're still surrounding it after it's been ovulated. So the egg probably is descending the oviduct, surrounded by a kind of haze of progesterone. So people looked at this ages ago and discovered that progesterone induces a very rapid response in human sperm, virtually instant in as much as one can detect. And the primary mediator of that seems to be a very sudden rise in intracellular calcium concentration, which is an intracellular message. And that was very interesting for a number of reasons, partly because it clearly had potential significance for fertilization, and also because it was not what one expected steroids like progesterone to do. But what we did find out in the meantime was that there is very good reason for thinking progesterone matters in fertilization. It regulates all sorts of things that we know are really important. And at last, they've given us a sort of clear, precise, mechanistic step involved in that, whereas up till now it's been a black box virtually.
So the sperm comes into contact with progesterone. What's the next stage? What actually happens?
Well, what progesterone does is induce an increase in the intracellular concentration of calcium ions, which are normally kept in cells very, very low. I mean, the cells spend quite a lot of energy mopping calcium up and pumping it out and keeping it very low. And rises in calcium concentration are used in every cell we know about as a conveyor of information, the size of the rise and the shape of the rise in terms of its kinetics, things like that. And in sperm, certainly calcium is very, very important for controlling how they swim and controlling a particular secretion event that they do called the acrosome reaction. And progesterone is sort of there as the sperm approach the egg. It may actually be there at very low concentrations other places as well, but certainly as the sperm swims right up to the egg, it's going to hit a wall of very high concentrations, and it seems to switch on all sorts of things. But progesterone is like a real sort of wake-up call. It presses a button and the sperm starts doing things.
So the presence of progesterone causes this sudden influx of calcium ions, or at least a lack of pumping it out. And that obviously is a key stage in changing the behaviour of the sperm cells.
Yes, I mean, we've known that the signal, the change in calcium concentration, was there for ages because there are techniques for measuring concentration in cells which are optical. And therefore they've been quite nice for applying to sperm because the fact that sperm are small and tend to move about a bit doesn't stop you making the measurements. And one of the things that's really key in this is what's in the Lischko and Kirchhoff paper, is that they developed a technique for applying electrophysiological methods that are used normally in recording the flux of ions across the membranes of nerve cells, and they managed to apply it to sperm, which are like an order of magnitude or so smaller, and very, very difficult for various technical reasons to apply these techniques to, and they made it work, which meant they could actually measure the flow of ions across the cell membrane. And doing that allowed them to be much more precise, to characterize what was going on, and to actually identify the fact that progesterone was activating a specific type of protein ion channel in the sperm membrane.
Does this particular membrane channel have any other role that we're aware of? Is it normally functioning in a very low level and then just gets ramped up by progesterone, or is it exclusively for this purpose?
Up until now, we knew it was there, and we knew it was exclusively expressed in sperm. So the channel's called catspur because it's a cation channel, and it's only expressed in sperm. And we knew from various experiments that had also been done on mice that functioning of this channel is very important in regulating the way the sperm swim. And if you produce mice where the gene that codes for this channel has been knocked out, they're still fairly healthy because the only thing that's not going to be working normally is the sperm. And the sperm look okay, and they can move and they can swim, but they can't undergo a specific change in the way they swim, which is called hyperactivation. And it's a much more kind of aggressive way of swimming, which is switched on as they approach the egg. And it seems to be there to provide a kind of added power to get them through the layers that surround the egg in order they can get right through and do the fusion event. And in mice that haven't got this protein, they can't do that change in motility, and the result is they're completely sterile.
So now that we've shed a bit more light on this mechanism, can we start to find ways to use it to our own purposes? Could this be the new contraceptive?
I think in principle it certainly should be. It's an enormous opportunity because this is completely specific to sperm and nothing else. If you can produce a drug that hits this channel and nothing else, then you've got a perfect contraceptive. The channel itself belongs to a family which is quite a large one of voltage-operated channels of various sorts, and certainly some of the other ones are quite similar in their structure, and so finding a drug that's really specific to catspur may turn out to be quite difficult, but I guess in principle it certainly should be doable. And if that could be done, then you could certainly produce a drug that would give you a really nice male contraceptive.
Steve Publicover from Birmingham University. You can read Steve's News and Views article along with the two papers he discusses in this week's edition of the journal Nature. Now, our human eyes may have blinkered us to the way that other species see the world, and understanding how birds in particular see could help to reduce the number of fatal collisions with man-made objects such as wind turbines, power cables, or even buildings. Writing in the journal Ibis, Graham Martin argues that to cut down on these deaths, we need to see the world from a bird's eye view. Sadly, collision with man-made objects seems to account for the largest unintended human cause of avian fatalities worldwide, and many bird species are prone to collisions with structures that do appear very conspicuous to us. For example, behavioural observations have shown that the white-tailed sea eagles that live in Norway show absolutely no tendency to avoid wind turbine blades. They simply treat them as if they weren't there. Although some research has looked at these collisions from the perspective of flight behaviour and manoeuvrability, very little has actually been published on the visual and perceptive aspects of this problem. Assuming that the visibility of an object at a distance is the problem, most collision-reducing measures that we've put in place in the last 30 years have basically involved marking an object with flags or with reflective balls, but the probability of a collision still remains very high. It's clear that birds don't see the world in the same way as humans. There are distinct differences in eyeball anatomy, in the location of eyeballs on the head, and in how signals are processed in the bird brain. Martin argues that in order to devise effective strategies, we must develop a sensory framework based around a bird's perception of the world. Now, we humans are used to the idea of being able to see directly in front of us. That's usually in the direction that we're travelling. But many birds are actually adapted for coverage alongside, above, and even behind the head. Now, this obviously can give them a much wider field of view, but it reduces the region of binocular vision that exists in the direction of travel. Now, lateral vision to the sides, may play an important role in the detection of predators or in foraging for food, but it clearly comes at the expense of being able to see where they're going. Even incredible birds like the peregrine falcon, whose vision is good enough to enable them to pick other birds out of the sky, relies mainly on this lateral vision. They actually view prey from the side, and they only switch to the front-facing binocular vision when they're at very close range. So what can be done to reduce collisions? Sadly, there's no catch-all answer, as what works for one species may be effectively invisible to another. But there are some general principles that might help. Very large, very high contrast markers that employ some movement should be deployed around an obstacle, both on the ground nearby it as well as actually in front of it. It may also work to redirect flight paths. This may be even more effective than marking out things as hazards. But above all, understanding more about the specific species that are at risk and how they perceive the world could help to reduce these accidents. And if you'd like to read up on anything we've covered this week, the references and transcripts for each of these news stories we've discussed are online at thenakedscientists.com/news.
Distilling the best science. The Naked Scientists.
You are listening to The Naked Scientists with me, Ben Valsler, and with Dominic Ford. Coming up, Brian Greene will be explaining how our universe might just be one of many, many multiverses. But before we get into anything, Dominic, I've had a great question here from Vince Mills. Now, he asks, if you were to send a probe like the ones that we send to Mars deep into the Sahara Desert, would you find evidence of life? And in particular, would you find evidence of us?
Well, that's a great question, because NASA do actually test some of their spacecraft in the New Mexico desert, or if they want a really harsh environment, they might try the Atacama Desert at high altitude in Chile. And that's a useful testbed for a couple of reasons. It provides a similar physical environment to what you might find, for example, on Mars, and so you can test for practical issues like whether your wheels are going to get clogged up with mud when you drive around on Mars. But it also means you can see if you can detect the really quite sparse life forms, the bacteria that you find in the sand of the desert. And the answer is that yes, you can. But you really need to draw a distinction between two different objectives that you can have when you're searching for extraterrestrial life. You can either be searching for anything that seems to be alive, so anything from bacteria upwards, or you can be searching for signs of intelligence, searching for intelligent life like ourselves. And you can divide the current search programs for extraterrestrial life into those two categories. So if you're sending rovers to Mars and looking at soil samples, you're really talking about looking for bacteria rather than looking for little green men. But if you're looking at the signals from radio telescopes to see if you can detect alien television signals perhaps coming from alien planets, then that is looking for intelligence rather than direct traces of the life itself. Having said that, I think if you were to land a rover in the desert, you probably would be able to detect that there was something quite funny going on this planet, because you would smell the air and you would notice it had quite a large oxygen content, and you would wonder where that oxygen was coming from, and thinking that maybe you needed some plants and some photosynthesis to make that oxygen. And you would probably also notice that this planet had quite a lot of radio noise coming from it, from planes, from communication satellites, and of course from radio and television transmitters. So you would think it was quite an odd planet, I think.
So the odds are it would pick up some very tantalising clues of our existence, even if it landed somewhere where there are no humans for hundreds of miles.
I think it would, yes.
Now, one of the most promising technologies for tackling rising carbon dioxide levels in the atmosphere is known as carbon capture and storage. Now, the idea here is that you pump carbon dioxide from power stations into a rock rather than into the atmosphere, but you do need to have the right kind of rock. To find out more, Planet Earth podcast presenter Richard Hollingham visited the pub.
It's the curiously named Ye Old Trip to Jerusalem. In the centre of Nottingham, it lays claim to being the oldest inn in England. Well, the pub is built into a sandstone cliff, and inside it feels more like being in a cave than a pub. A cave with beer. I'm here to meet Mike Stevenson, the director of the National Centre for Carbon Capture and Storage. Mike, why have we come to the pub?
It's a great place to show you how we can use these rocks to actually absorb carbon dioxide. We can take carbon dioxide out of the atmosphere and push it or force it into these rocks. And we think it could probably stay there for a very, very long time.
Now, I had this idea in my mind of carbon capture and storage, that it was using reservoirs underground, vacant spaces in the rock, like tanks that you could inject the carbon dioxide into, but that's not the case?
No, it's not like that at all. There are very few open spaces if you go down deep into the rock. The pressure's too big to get open space. But what these rocks illustrate quite well is that there are a lot of very small spaces between the particles that make up the rock. So, for example, if I just show you that very quickly, just a demonstration, if you put a little bit of beer, there you are. Be careful not to pour too much on, but if you pour a little bit of beer on the sandstone, which is the wall of the pub, what you see is it's all wet and shiny at first, and then what you slowly begin to see is the beer is soaking into the rock there.
It's disappearing very, very quickly, isn't it? And now it's almost dry, isn't it?
Gone, yeah.
I suppose that's like a beach, isn't it? When you step on it, you get the water there, then
Yes.
it goes dry very quickly.
That's right. What you've really got here is the sandstone itself is made of particles, more or less spherical particles. They're all packed together. They're not packed together perfectly because there are spaces in between. And when I'm pouring the beer in there, what's really happening is the water, the beer, is leaking into or soaking into these spaces in between the particles. You can't see them, but there is a huge amount of space inside this sandstone. And that's what we propose to do, fill it up with carbon dioxide.
How would you do that? It's very easy to drip beer on a little bit of wall. It's quite different to inject carbon dioxide.
If you do it right, you should be able to push it into this rock quite effectively. This has been done for a long, long time. For example, in the United States, they've been injecting CO2 into rocks for 30 or 40 years, actually for enhanced oil recovery. That means squeezing the last bit of oil out of an old oil reservoir. So we know how to do this, and we think we could probably store quite a lot of CO2 in this particular rock. This is another reason why this pub is interesting. And this bunter sandstone underlies a lot of the North Sea and the Irish Sea, and these are the places where we might put the CO2. So you're actually looking at the rock that underneath the North Sea would be our storage space.
Now, you dribbled the beer on a couple of minutes ago. It's almost disappeared, but some of it's come out. How do you ensure that your carbon dioxide stays there?
The main thing is to have the right kind of structure that will keep the CO2 in place. CO2 is a buoyant fluid when it gets injected at that depth, and it will tend to rise up above the water that's also in the rock. So it'll tend to float up. And the key really is to making sure that the rocks above the reservoir or above the sandstone are completely impermeable. It's a bit like a damp course in a house. We're talking about a rock layer that stops the CO2 going up any further.
So when is this going to happen? Are we on the cusp of this technology being available? So we start injecting carbon dioxide into these areas?
The key thing is that although all the three types of technology, there's the capture, which is really a chemical engineering activity, the transport, which is putting it through pipes, and the storage or the injection into rocks, all those three things are known about, and we've been able to do them for a long time separately.
And just to clarify this, the capture would be from, say, a power station or
Yeah,
something
generally
like that.
we capture from power stations, but there's no reason why you couldn't capture from a cement works or from an ammonia factory. All of them produce a lot of CO2.
Okay, so you've got all those in place, but
the problem is that the sheer scale at which we have to do this is something that is daunting, and also putting it together into a system that works, where one thing feeds another, not too fast, not too slow. That's a big challenge.
That was Mike Stevenson, the director of the National Centre for Carbon Capture and Storage, and he was talking to Planet Earth podcast presenter Richard Hollingham over a pint. And you can download the latest Planet Earth podcast as well as other Planet Earth online resources at thenakedscientists.com/planetearth.
Laying the facts bare. The Naked Scientists.
This is The Naked Scientists with me, Ben Valsler, and with Dominic Ford. Now, parallel universes sound like an idea straight out of science fiction, but they are genuinely based in fact. In the best mathematical models we have to explain the universe, they often predict some form of multiverse may exist as well. Brian Greene, Professor of Physics and Mathematics at Columbia University, examines 9 different multiverse proposals in his new book, The Hidden Reality. I caught up with him at the Cambridge Science Festival.
We're asking one of the grandest of all questions, which is our universe the only universe? And that, at first sight, is a strange question because we're used to thinking of universe to mean everything, the totality. But a lot of research from a variety of different directions over the last few decades have suggested that what we long thought to be everything may not be everything. It may be a piece of a larger whole. And that larger whole may contain other universes. And that's where we come to the idea of multiple universe.
There are actually quite a few different theories born of, largely from the maths. How do we try and tie them all together? Are they at the moment just competing ideas, or are they all actually pieces of one larger jigsaw?
Well, in my book, I actually describe 9 different variations on the theme of multiverse. And there are relationships between them, but we have not yet developed any kind of meta-multiverse framework in which all of these proposals would sit. They're not necessarily mutually exclusive. We don't know if any of these are right. We will only know that when there's some experimental or observational evidence. But we're taking the idea seriously because our mathematical investigations lead us to this idea. We don't impose this idea from the outside. We follow the math, see where it takes us, and time and again, it's suggesting that there may be other universes.
Following the maths is obviously a very good way to get at what may be objectively the truth, but trying to understand these in human terms is very difficult. It's very counterintuitive. How do you get around trying to explain to people what the results of these numbers might actually mean?
Well, a number of the multiverse proposals are not that hard to grasp. For instance, we all know of the Big Bang, right? We have been trying to understand the Big Bang with greater precision in recent decades than we did in the past. In essence, we've been trying to fill in a missing piece of the Big Bang theory, which is what started the bang. What was the bang? What started space to undergo this outward swelling? We now have a proposal on the table. It's called inflationary cosmology. The name is not all that important, but I bring it up because when we study the math of this proposal, it suggests that the Big Bang may not have been a unique one-time event. There may be many Big Bangs, each giving rise to its own swelling realm of space. It's as if our universe is a growing bubble in a grand cosmic bubble bath with other universes. That is a strange idea, but it's not that hard to wrap your mind around this possibility, and this is one of the proposals that I discuss in the book.
As well as looking at things on the grand scale of the entire universe, we have to consider things at the subatomic scale, smaller than we currently know about. How does that fit into the idea of looking at parallel or multiple universes?
Well, you wouldn't think that it would. When studying tiny things, molecules, atoms, subatomic particles, that would not suggest that you are en route to a theory of parallel universes. But surprisingly, we have found that it does lead to that possibility from a number of different perspectives. Let me just give you one. So quantum mechanics, the study of the smallest ingredients in the world, broke the older Newtonian model of the world by saying that you can't predict with absolute certainty the result of any experiment. You can only predict the probability of getting one outcome or another. The electrons say 50% chance being here, 50% chance of being over there. Now, that's weird enough, a world governed by probabilities, but a puzzle that still persists to this day is when you do a measurement of the electron, you find it at one location or another. So what happened to the other possible outcome? One suggestion is that it happened too. You saw the electron over here in one universe, but the math suggests that there was a copy of you who sees the electron over there in another universe. Two universes coming from the probabilistic framework of the quantum world, multiple universes.
So would the implication of there being multiple universes be that there are actually lots and lots of me pointing lots and lots of microphones at lots of you all throughout this multiverse with very, very slight differences between them?
It's quite possible. In some of the multiverse scenarios, exactly that would happen. For instance, in perhaps the simplest of all multiverses, it comes from imagining that space goes on infinitely far. We don't know that it does. Maybe it curves back on itself like the surface of the Earth, but if it does go infinitely far, there is a breathtaking conclusion along the lines of what you just mentioned, which is this. In any finite region of space, matter can only arrange itself in finitely many different ways. It's like if you take a deck of cards. This is my favorite analogy to describe this. If you shuffle the deck, the cards come out in different orders. But there are only finitely many different orders for the cards, so if you shuffle the deck enough times, the order of the cards must repeat. No way around it. Similarly, if space goes on infinitely far, then the order of the particles, region by region by region, must repeat too. There just aren't enough different arrangements to go around. Now, you and I were just an arrangement of particles. If the arrangement repeats out there, then we are having this conversation out there. And like you say, it's even easier for the particle arrangement to almost, but not exactly repeat. That would mean that perhaps I'm interviewing you in one of those universes. So it's a startling idea, but it comes from simple assumption. Space goes on infinitely far, and also hidden assumption as well. The laws of physics that we know about here are the laws of physics everywhere, so that we can actually say something sensible about what happens out there. But under those mild assumptions, you come to this startling conclusion.
How can other areas of science actually play a part? We've already mentioned cosmology, we've mentioned astronomers, we've mentioned particle physics. How are these different groups all feeding into finding the same answer?
Well, I think the different groups play different but overlapping and complementary roles. When we talk about multiple Big Bangs, this comes from inflationary cosmology, which makes some predictions that observational astronomers can look to the sky and try to test. Inflationary cosmology says some very definite things about the microwave background radiation. This is heat left over from our Big Bang. It speaks to tiny temperature differences in the sky that inflationary cosmology implies should be there. The observational astronomers turn telescopes skyward, and they have found those tiny temperature differences in the sky, confirming one prediction of this approach. And then when those ideas also suggest something else that may seem more far out, like multiple universes, we're compelled to take that idea seriously.
What do you think will be the next stage? What do we need to do to get a bit further with this work?
Well, I think there are two major directions. One, we need to understand the mathematical underpinnings of all of these ideas with yet greater precision. That is vital in order that we can make more precise statements of what experimenters and observers of astronomy should find. And then on the experimental and observational front, we need to keep pushing onward. I mean, the Large Hadron Collider is a device that may give us a lot of insight in the coming years. Some of the parallel universes proposals do come out of string theory, and we need to see whether string theory is right or wrong. There's at least a chance that the Hadron Collider could give us some insight, looking for supersymmetric particles, a class of particles that string theory says should be out there, but we've not seen. The idea of extra dimensions, which comes from string theory. The collider actually has a chance of finding them. How? Slam two protons together. The equations show that some of the debris created in that high-energy collision can be ejected out of our dimensions into the others. How would you notice that? The debris would take away some energy, which means our detectors would measure less energy after the collision than before. So there's a real possibility for some interplay between experiment, observation, and theory, and they all need to go forward hand in hand.
That was Brian Greene from Columbia University. Now, as Brian mentioned, any hypothesis on multiverses will remain just that, a hypothesis, until experimental physicists can find observations to support or refute these ideas. We're joined in the studio now by Dr. Chris Lester. He's a Cambridge University physicist who also works on the LHC Atlas instrument. Thank you ever so much for joining us.
Thank you.
Brian mentioned supersymmetry, so before we go any further, could you just explain what that actually means?
For supersymmetry is a fairly old theory. It's been around since the 70s or thereabouts. You could think of it as effectively a bit like when you take matter. We all know about matter, and we were aware also that there's antimatter. It's a sort of a reversed copy of the first. So the charges are all different, okay, and pluses and minuses and so on in antimatter. If you could flip all of those things again and imagine creating another mirror image of the world's particles, but instead of changing the charges, if you change the spins of particles so that the particles that had to be spinning originally aren't, and the particles that aren't spinning now have to be, then those are your supersymmetric particles. And there are various sort of reasons for wanting those, including some of the particles that you get out of that could perhaps make dark matter and things like that the astronomers are telling us that we need.
Antimatter originally arose as what looked like an error in the maths. Are we getting something similar with supersymmetry? Is this something that sort of has to be there to make things balance, or is this something that is key to the predictions of the theories?
Well, at the moment, we don't have to accept supersymmetry at all. It may simply not be there. But many of the reasons that people are, or those people who are hoping that it's there, one of the reasons that they want it to be there is certainly because it fixes up a number of problems in the maths that they don't like. That sort of thing has been useful in the past, and antimatter turned out to be true. Whether that's going to be the case for supersymmetry, we don't yet know.
So where are we now with the LHC experiment? It's obviously had its first run, and it's currently cooling down. They'll be switching it on again fairly soon, I think.
In fact, well, it turned on again about a week ago.
Right. Well, yeah. I apologise for being late in that case. Sorry, LHC. So it's now back on for its second batch. But what have we got from it so far?
With the first year of data, that's the data taken in 2010, the machine was effectively finding its feet. Every couple of weeks or so, the people who run the machine and get the collisions were able to make it almost 10 times, twice as powerful in every sort of 2 weeks. So all the data from last year, in a sense, is almost exclusively the data that was taken in the last couple of weeks of operation. And with that data, we've been able to start closing in on the Higgs boson, finding out, not yet in a position to say whether it doesn't exist in any particular places, but closing in on it. Trying to find out whether supersymmetry exists. This is the work that I've personally been doing, and we've managed to show that quite a lot of the places where people thought supersymmetry might exist, quite a lot of those simply are unlikely to be true, could still be hiding in various places. In a sense, with the data that we've taken, the limited data from last year, the Large Hadron Collider has been, in some sense, just rediscovering the standard model, getting to the point at which it's about to be able to make even more important and exciting predictions.
Specifically, you work on Atlas. It's very easy to fall into the trap of thinking that the LHC is just one big experiment, but there are actually lots of different detectors on it. Specifically, what is Atlas doing?
Atlas is one of the two general-purpose detectors. So, as you said, there are 4 main detectors on the Large Hadron Collider. 2 of them have specialist roles. Atlas is trying to basically look for anything. What are the sort of basic building blocks of the universe? We're looking for any particles we don't currently know about. We're looking to find the Higgs boson, and we're trying to sort of cover all bases, really. So it's a general purpose experiment that just is looking for things that are out there that we haven't, that we're not yet sure about, that we don't know exist yet.
Does this mean that you're getting pulled every which way by different people demanding your data and interpreting it in different ways? So you'll have theoretical physicists saying, well, I can use this data to find these hidden dimensions. You'll have the particle physicists saying, I'm going to confirm or refute the existence of something very obscure. Do you really get to concentrate on one particular hypothesis for yourself, or are you having to do a very general interpretation of these figures?
Personally, I do get to, and most of the people working on Atlas do get to focus on a fairly narrow area, the area that interests them most, because quite simply there are so many people who are working on it to cover all of those bases, that everyone sort of divides up the work amongst themselves. But even so, even in my case, where I was chatting to some of the theorists in CERN before our data was released, when you're still having to be quite secretive about what's there, so that the competition don't find out about it and use it. Very often those would be saying, but why aren't you working on this? Why isn't your first paper on supersymmetry ruling out this particular type of supersymmetry or that type? So yes, there's lots of tensions there. People intrigued to convince us to work on their particular bit.
Have any of the LHC results so far, obviously it's still early days, has anything actually told us that what we thought was right is actually wrong? Rather than making big new discoveries, have we found out that our theories didn't quite stand up?
Not that I'm aware of so far, no. Well, there are some little hints in some places of things where effectively I think the juries are still out, and we need to take more data and we look at what's coming on early next, what is now this year. But I think at the moment you could still say the standard model rules okay. Our current ideas about particle physics haven't yet been shown to be completely wrong in any particular area.
Well, Chris will stay with us for the rest of the show, so if anybody has any questions for him or for us, then do get them in now. You can tweet at Naked Scientists or email us, chris@thenakedscientists.com. But now, keeping on the theme of particle accelerators, for this week's Naked Engineering, Mira and Dave have been out to the Diamond Synchrotron, that's an electron accelerator, based out in Didcot in Oxfordshire, where the head of engineering, Jim Kay, gave them a tour of the facility to see just how electrons can be made to move close to the speed of light, using a combination of vacuums, magnets, and a few other pieces of engineering.
The Diamond Synchrotron is a large-scale science facility comprising 3 electron accelerators, which are used in series to produce electrons which are stored in our storage ring at 3,000 million electron volts. And at that energy, when the electrons are bent in their orbit, they produce high-energy X-rays. We extract the X-rays in tangential beam lines to the storage ring and convey them down to end stations where the scientists have positioned their sample to expose the sample to X-rays and take data on how the X-rays interact with their samples.
The storage ring itself is very large. It has a circumference of 560 metres and the electrons are moving very close to the speed of light. So how, firstly, do you even get electrons moving that quickly?
Okay, the electrons start the journey in a cathode, and in the cathode we boil electrons off a heated surface in a vacuum and then attract them towards a positive plate, the anode, which is held at 90,000 volts. We then inject them into a device we call a LINAC, a linear accelerator, where now the energy is added to, but by using RF waves. These RF waves are radio frequency waves, and this is a different method of giving energy to the electrons. And in the LINAC, we accelerate the electrons now from 100 keV to 100 MeV, 100 million electron volts.
So this is essentially producing waves of electric field in a chamber. So little bunches of electrons will kind of surf a wave down the chamber and accelerate down the chamber.
Well, we're now within the synchrotron itself, so we're just towards the end of the LINAC, the linear accelerator, towards the booster section of the synchrotron.
So we're stood in the booster tunnel, which, as you can see, is a large concrete vault. And in fact, here the walls and roof are 2 metres thick to absorb the harmful radiation that's produced when electrons are circulating, and to keep the dose on the outside of the walls no higher than background.
We've now moved away from the booster into the main storage ring, which is where the electrons move to after the booster section of the synchrotron. We're now next to an insertion device, which is actually where the electrons are made into actual X-rays, Jim.
Basically, the way we produce high-energy X-rays is that we expose the electrons to an alternating magnetic field, and we produce this by having many permanent magnets which we bring close to the electron beam and arrange them so that the electrons see an alternating north-south, north-south, north-south field. And as the electrons go through this alternating magnetic field, they wiggle or move side to side. And every time a relativistic electron wiggles, it gives off a squirt of X-rays.
This is a bit like when electrons wiggle up and down an aerial, they go off radio waves, but it's happening far faster, so now it's X-rays.
Well, this insertion device it's a very large structure. It's about 3 metres tall good 2 metres or so wide. It's very solid looking.
This device carries these magnets, which we bring very close to the electron beam. The closer we can bring them to the electrons, the stronger the magnetic field, the bigger the kit we can give the electrons. So that's good to produce the high-energy X-rays.
You're talking about the magnets having to be incredibly accurately positioned. Why is accuracy so vital?
So what we're trying to do is produce a spot of electrons, a focused spot of electrons, 10 microns diameter. So that's a quarter the diameter of a human hair. At that dimension, so many things can upset the stability of that electron beam. So in terms of the stability, we know that at the beam height, which is 1.4 metres above the floor, if the temperature in here were to change by 1 degree C, that beam height would change by more than 20 microns, which is more than twice the diameter of the electron spot size. So we know that to keep the temperature very stable in here is key, and hence you can see all this heating and ventilating ductwork providing air at 22 degrees C. You can also see that the electromagnets, these very big red and yellow magnets, which have water-cooled coils because of the current density that we need to drive these magnets. And the water cooling is also provided at 22 degrees C. And hence, by the air being at 22, the water's at 22, we minimise the heat transfer and hence the contraction and expansion of all these metallic components.
So stability is clearly a key engineering challenge with regard to diamond, and the minimisation of any movement, really. At regular intervals around this storage ring, there are surveying points, maybe every 10 metres, which are, I imagine, then just making sure that nothing's moving.
As you can imagine, as we look down the tunnel here, we can see it very quickly curve out of view. But we're trying to align each of these girders carrying these magnets to within 0.1 millimetres of its neighbour. And around the whole 560 metre circumference, we're trying to align everything within a global cylinder of confusion of 1 millimetre diameter. And in order to do that, we've got a very accurate survey network using some very precise theodolites and a process of automatic target recognition when we carry out a survey to position these magnets with such high precision.
Well, another factor to consider for the stability is actually the ground that the synchrotron is on.
Yes, very true. And we've built a very strong floor that carries the accelerator and all the beam lines that are linked to the accelerator. We want to guarantee that the X-rays produced at the focal point of the electrons have the best chance of getting to the sample point, maybe 40 metres or more away, and not lose any definition or be blurred by vibration or by differential settlements. So the floor we've built is 800 millimetres thick under our feet here and carried in the whole facility on over 1,500 piles, which are 600 millimetres diameter and penetrating down to 15 metres into the chalk. It's extremely stable, and we've used a system called a hydrostatic levelling system, where over a 60-metre length we've been measuring the level of the floor, accurate to a few microns, over the last year. And we know now that over 10 metres our stability has achieved our 10 microns per 10 metres per day stability requirement.
And that's a very high level of stability indeed. That was Jim Kay, Head of Engineering at Diamond Light Source, showing Mira and Dave the design and workings of a synchrotron and the importance of stability when precision is required on the micron scale. This is The Naked Scientists with Ben Valsler, with Dominic Ford, and we're joined today by Dr. Chris Lester from Cambridge University. Chris, we've had a question come in on Facebook that hopefully will be your sort of thing. It's from Ryan Chown, and he wants to know what the scientific progress will be when we confirm that the Higgs boson really exists.
Well, if we do confirm it exists.
Of course.
It would be, of course, a stunning intellectual achievement from the point of view of people across the world having had to get together and work for more than 40 years on trying to actually track down this one particle. But in one sense, if that real number is found and we learn that the particle's there after all, and many people think that it is, that would in some sense be perhaps less stunning than looking throughout the lifetime of the Large Hadron Collider and checking all the bases and then finding out that the Higgs boson didn't exist, which would really put a cat among the pigeons. So in a way, there are some people, mischievous people perhaps, who would most prefer that we didn't find the Higgs boson, so long as the machine carries on working and it's a definitive not having found it.
You said put the cat amongst the pigeons. Are there good alternative hypotheses that would step in to fill the gap, or does it really send our current understanding totally into the bin?
There are competing theories that would try and step into that void. But the problem, perhaps, is that none of those has really got a strong following. But there's many things we've built on top of the Standard Model and upon extensions of the Standard Model which help explain the universe and the way it works. And that there isn't that similar edifice built on top of these other theories. So there'd be a lot of thinking still to do to make them all work.
Okay, thank you. Dominic, we've had this one in from Tom Ristola. Now, he says, given that the heaviest elements are forged during a supernova, or certainly throughout the life of a star, is it theoretically possible that there could be heavier naturally occurring elements that we don't even know about if there was a star that was big enough to forge them?
Yes, but it is quite an awesome thought that all of the heavy elements in the universe were made in the nuclear furnaces inside the centres of stars. So all of the carbon that we're made of and all of the oxygen in the atmosphere was all made in the centres of stars and then blown out of those stars in supernova explosions subsequently to form into the solar system. Now, the more massive a star is, the heavier the elements it makes and the more heavy elements it makes, and the bigger the supernova explosion at the end and the more widely distributed that material is. But in terms of heavy elements that we don't yet know about, what you find is that the heavier an element is, the more unstable that atomic nucleus is, and the more radioactive it is. So, for example, uranium is quite a massive atom, and that is, of course, radioactive, and we use that as a power source. As you move to more and more massive atoms, the lifetimes of those radioactive elements goes down, and you start to find that your average decay time is less than a second, or perhaps only a millisecond. And so even if those atoms were formed, they wouldn't last very long, and we certainly wouldn't find them in the universe.
Do you think it's likely that we would see evidence of them having existed, maybe the energy from their decay?
I think some of the atoms which people have been making in the lab, as I say, have lifetimes of order milliseconds. So that is really so incredibly short that it would be very difficult to detect any signature at all.
I'll put this to both of you, that's okay. Nirav Bansali said he was looking at string theory and came across the idea of there being more than 3 dimensions. In fact, some theories suggest 11, some up to 26. But he wants to know how they'd fit in our universe. We only have a few seconds left, but do you want to have a go?
Well, I think the thing you have to picture is a lot of these things they would fit all around you. Every part of your fingernail would have a latitude, a longitude, and a position in some of the extra dimensions, at least in some of the classes of theory. There are others where the extra dimensions only gravity can fit into, in which case you still only have a latitude and longitude and nothing else, or a Z position.
So you can imagine our three-dimensional universe as being a sort of sheet in a much higher dimension of universe.
Excellent. Well, this is brain-bending, unfortunately, for me, but hopefully you guys at home will ask some great questions about it. And speaking of great questions, it's now time to join Diana O'Carroll with our question of the week.
This week, when you wish upon a star.
My name is David, and I'd like to know, how do we measure the distance to the nearest star?
For distances as great as interstellar ones, we need something a bit more specialised.
Hello, my name's Simon Singh, and I'm sorry I'm whispering, but I'm here in the Houses of Parliament as we get ready to launch our libel reform bill, but that's a whole other story. I'm also the author of Big Bang, and I suppose I'm here to try and explain to you how we measure the distances to the stars. Now, the way you do this is by using something called parallax. Now, that means that you measure the angle to a star using a telescope, and then you move your telescope to a different position, and you look for a shift in the angle to the star. Now, the problem is the stars are so very, very far away, you need to move your telescope a long way in order to get a perceptible shift in angle. And a few meters, a few kilometers, a few 100 kilometers just isn't enough. And it wasn't until the 19th century that an astronomer, Friedrich Bessel, moved his telescope to the other side of the sun. He took a measurement in July from the Earth, and then he waited 6 months for the Earth to go right round the other side of the sun. He took another measurement, and even though the Earth and his telescope had moved such a vast distance, the shift in angle to the star was just 1/6000th of a degree, a tiny shift. But that tiny shift was enough for him to work out the distance to the local stars around us. Now, to give you an idea how far away those stars are, it takes about 8 minutes for light from the sun to reach us on Earth. It takes over 4 years for light from our closest star to reach us. And that's how you measure the distances to the stars.
Parallax is great for doing what is essentially a giant and time-consuming triangulation. Gold star goes to forumer Astrogazer for his response, which was very similar to Simon Singh's model answer. Next week, we're sticking with astronomical bodies.
Hi, Naked Scientists. This is Taylor Sharp from Vancouver calling, and I had a question about the Earth and gravitational forces. I'm wondering which part of the Earth experiences the most and the least gravity, since as you move closer to the center of the Earth, gravity reduces to almost zero. Thank you very much.
Where would you least like to get out the bathroom scales? Answers to Chris at thenakedscientists.com, or write them down on the forum, and that's at thenakedscientists.com/forum.
Thank you, Diana. So if you've got any ideas where is the worst place in the world to weigh yourself, then do get in touch. Drop us an email to chris at thenakedscientists.com with your ideas. Now, that's actually all we have time for on The Naked Scientists this week. Many thanks to Steve Publicova, Brian Green, Chris Lester, and our production team of Mira Senthalingam, Dave Ansell, Diana O'Carroll and Tom Simpkins. Next week, we're exploring life in inaccessible places. We'll find out how whole ecosystems develop in the absence of light, down at deep-sea vents, and deep in subterranean caves. If you've got any questions for us, then tweet at Naked Scientists, write on our Facebook wall, or email Chris at thenakedscientists.com.
The Naked Scientists comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the Natural Environment Research Council, and UK FAST. For more information, look us up online at thenakedscientists.com.